All right. So, guys, when we're doing stoichiometry, one of the things that you guys are going to have to learn how to do is if you see a problem like this, you're going to have to learn how to, number one, write the chemical balance, the chemical equation, and then balance it. Okay? So we kind of started doing naming yesterday, so I want to jump right into stoichiometry today. Some of these things are going to be easy. Some of these things are not going to be as easy. If you have a calculator, maybe a good idea to get it out. If you want to go ahead and come grab one of these, hang it on my door. I'm going to pause the video and let you guys grab that real quick. So, number one, when sodium hydroxide reacts with carbon dioxide, it produces sodium carbonate and water. When 10.23 grams of sodium hydroxide is used with an excess of carbon dioxide. Now, for the video this summer, you should be screaming for joy for that word right there. Why? You know what the limiting reactant is now. You don't have to find it. So, since 10.23 grams of sodium hydroxide is used with excess carbon dioxide, you know that sodium hydroxide is the limiting reactant. What mass and volume of water is produced? Now, that's an interesting question there at the very end, and I love this question for that very fact right there. So the first thing we need is a balanced equation, because would you agree that we're going from sodium hydroxide to water? What is the only way to compare two different substances? Mole to mole. We've got to get to our mole to mole first. Okay? So, what unit has been given and what unit has been asked to be found? What unit? Grams to grams. Okay? Alright, so the first thing we need is a balanced chemical reaction. So in sodium hydroxide, what's the formula? NaOH reacts with carbon dioxide, which is what? CO2. It produces sodium carbonate and water. So I'm going to go ahead and write the H2O over here because that's the easy one. The other one is sodium carbonate. You take 1 second and write it down. Sodium carbonate. Is that what you got? Good deal. Right, next. Anytime you write a reaction, what do you also have to make sure of? It's balanced, okay? Now, obviously, I know the first thing I'm probably going to have to add is a 2 right there. Right or wrong? Right. Does that balance it? Got it again. All right, let's do the easy one first. Our hydrogen's balanced. 2 and 2, right? Oxygens. I got, and I'm going to just do it right here. I got 2 oxygens here. I got 2 oxygens here, so that's a total of 4. I got 3 oxygens here plus 1 oxygen there, so a total of 4. So it is balanced. Okay, cool with that? All right, so then we got to start with our given. They give us 10.23 grams of that stuff. We don't even need to worry about that. And they're asking us about mass and milliliters. Okay, do you agree the question said mass and volume? Okay, so let's start with the way we know, with the one we know first. Let's go gram to gram first. So I've got, I'm going to start way over here. So 10.23 grams of NaOH. And if you noticed, and in the videos I think you probably noticed as well, what did I get rid of from last year when setting up these steps? I got rid of the parentheses. I do that in honors just because sometimes people need the visual stimulus of that. It is a completely separate step. You guys should be to the point now where you don't need that. That's a waste of time with pencil lead. Okay, you don't even have to put the X's if you don't want to. Okay, but the content within the step is important. So we know we got to get rid of grams of NaOH. So where's it got to go? On the bottom. So let's change it to pink. So we're going to grams of NaOH, and what do we got to go to? Moles of NaOH. We want to get rid of that. So mole of NaOH. I may not know where I'm going, but I know I got to get rid of that. And I'll pause for just a second and let you guys catch up with me. And I asked this question at the very beginning. We're going from sodium hydroxide to water, and we have to go through what to get there? Mole to mole. Am I at that step? Yes. Okay. So I can finally go to moles of water. Why can I not stop right there and answer the question? It asks for grams. Okay, you can't stop just because it says that. So we got moles of H2 on the bottom, and I need to get to grams of H2O on the top. Now let's fill out the numbers that are easy to fill out. Anytime mole was with gram, what does it get? 1, and anytime mole is with gram, it gets a 1. Where does your mole to mole step come from? Coefficients. So what is top to bottom? 1 over 2. Very good. I only asked you guys to memorize one mass of a compound, and that was water. What is the correct mass of water? 18.02. That's the only mass of compound that I'm asking you to memorize. Throughout this year, we will use carbon dioxide. We'll use sodium hydroxide. We'll use a few so many times that you'll eventually memorize those masses as well. But for this case, sodium hydroxide, anybody calculated it? 40 even. Yep, 40 even. 40.00. The way that you can know that is sodium is 22.99, oxygen is 16 even, and hydrogen is 1.01. So the 99 plus the 0.01 gives you the even 0 values, and then the 22, 16, and 1 give you the 40 value. So from here, it's a simple mathematical calculation in your calculator. Multiply across the top, divide by the bottom. Now, before you give me the answer, how many pieces of numerical data are given in the stem of the question? How many? No. How many pieces of numerical data? Just one. The only numbers they give you are 10.23. So that answers my second question. Your answer must always be given the correct number of significant figures. Well, you only have one piece of information. How many significant figures are in that number? 4. Okay, so your answer must be also given in 4. So what was the correct answer they gave you? Let me change this. You know what? I'm so mad at myself. I haven't put my fancy calculator on this new computer yet. Now, I'm only going to say this today and today only. From here on out, I expect you to just do this. Can you leave it just like that? You have to have 3 things in every answer that you ever have, especially doing stoichiometry. You got to have the correct number of significant figures to your answer. You have to have the unit at which they're asking you for, and you must have the compound formula of which they're asking it for. You have to have those 3 things. So we've got our 4 sig figs, and we have grams of H2O. Now, a lot of you look at that next part of the question. First of all, let me stop there. Any questions about that? I think that's pretty easy, straightforward stoichiometry, right? Okay. Now, let me ask you something. If you were sitting here this time last year, that would have looked like complete Greek to you, right? That would have completely blown your mind the 4th day of school last year. So be proud, and I don't want you to think, oh, well, this is easy. You're right, it is easy. You've come this far. People, if I show this to my next period class, they would just give up and quit and leave. Okay, but you're to the point where this is simple because you know the procedures. It's not going to get any harder. You just have to learn the procedures. Yes, sir. 304. Okay. See, one thing you guys will learn is that I rely on your accuracy for these calculations. Those of you that had me last year, you know I have a fancy schmancy calculator that I normally use, but I have not put it on this new computer yet, and I'll get it downloaded this week sometime. All right, so let's move on to the next question. So it says, what mass, which we just did, and volume of water. There is a key part to this that if you know this, please do not say this out loud. I am kind of fishing for a deep thought right here. Excuse me. Mass and volume of water. There's an interesting little tidbit that I threw at you a really, really long time ago. You can actually calculate this using stoichiometry. However, you do not have to. Why, Trevor? Perfect. This is a fact that you guys must know because you're going to see that type of question a lot. 1 gram equals 1 milliliter, which equals 1 cubic centimeter of H2O. This is the standard that everything was compared to. Okay? This was the standard that everything was compared to. So if they ever give you mass of water, you automatically know the volume. If they ever give you the cubic centimeters of water, you automatically know the volume or the mass. So this is something that has to be ingrained up there. Is this true for alcohol? For vinegar? Hydrochloric acid? No. Only for H2O. This is a trick question. Stay with me. Is it true for tap water? Not experimentally. No. Only for pure distilled H2O. There's something else. There's one other thing. So, going way back, what is density? Okay. So, what is the density of water? 1. 1 gram over 1 milliliter equals 1 gram per milliliter. That is also the density of water. Okay? It is pretty convenient, isn't it? Right? So, here's a trick question. If you have, should have said that. If you have 30 grams of water, how many milliliters do you have? 30. What's the density? 1. Okay? Don't let that get you. Because it's 30 divided by 30, which is 1. The density of water is always 1. Okay? Alright. We go with that. Spectacular. Alright, number 2. Perv nerd. Alright, so if 23.4 grams of aluminum nitride react with 10.3 grams of water to produce aluminum hydroxide and ammonia, what is the percent yield if only 2.15 grams of aluminum hydroxide is recovered? Wow, what a question. Okay, let's start with the basics. What is the minimum first thing you have to have? A balanced chemical equation. Start there. Try that. See if you can get the balanced chemical equation. Is that what you got? Okay. Now, the thing that kind of looks the weirdest up there to me, you know water, you know ammonia, you know hydroxide. The weird one's the first one, ALM. Why are there no subscripts in that? They're both 3. 3 positive, 3 negative, they should cancel. So that kind of wipes that one out. Alright, so I'm going to start with the end and work our way back to the beginning. Okay? It says, what is the percent yield? And I wouldn't write this right up underneath this. I may want to go down a few lines if you're writing this, because this is where we're going to come back to it. So we need to first discuss this, just out of curiosity, because I cannot remember. Was any of these type of problems in the summer videos? Okay, fantastic. Good. So, does anybody remember what percent yield is? Very good. Actual over theoretic, and then what? Very good. Times 100. So A over T times 100. So the thing about it is actual must be given in a problem, or you could theoretically do it in an experiment, because it's an experimental, it's an actual value. And theoretical must be stoiched. It's a verb now. Stoichiometry is. Stoiched? No. It must be stoiched. I could say calculated, but then you would say, well, how do you calculate it? You stoic it. So we're going to verb it. Okay? It's something you do now. You stoic. Okay? Can you use it in a sentence, please? What's the language of origin? That is actually interesting. I don't even know what the language of origin is. So what we're going to do is, if you go back and look at the question, it says, what is the percent yield if only 2.015 grams of aluminum hydroxide is recovered? Now, the word actual is nowhere in this question, but is it implied? Yes. Is recovered is an implication that you did something to get it. Okay? So that is something that we're going to have to learn how to do, is reading for value and reading for content. because some of these questions are not going to be verbatim of what you need. You actually have to read through the way they're asked. So that is implied that that is your actual value. So if we go back to percent yield, would you agree that we are searching for this value? Sorry, that did not work out how I wanted. We're searching for this. That's the question. What is the percent yield? This, we're good. We're missing two of the three variables. Well, one is the end result, but we're missing the theoretical. So we got to stoic to find it out. Okay. So the problem is, how do we stoic? Okay, you stoic. All right. So we've got 24.3 grams of this stuff, and we've got 10.3 grams of that stuff, and we're trying to find the theoretical of aluminum hydroxide. So that's going to be the issue. Now let me ask you something. Nowhere in there does it tell you that you need the grams of aluminum hydroxide, but again, how is it implied? Which is in what unit? Grams, exactly. The grams have to, the units have to match. So if the actual's in grams, the theoretical must be in grams. Is it possible to do a percent yield in moles? Sure, as long as, because no matter what, or the ratio is going to be the same. Exactly, so you're good there. If it gave it to you in moles, stay, but not, you have to continue. Question. Yes, sir. Hold that thought, that's where we're going. So, my question, if he did not ask that question, is I've got so many grams of aluminum nitride, I've got so many grams of water, and I have to get an aluminum hydroxide. Which one do I pick? You don't know yet. That's the issue. You got to find the limiting reactant. So hopefully you remember this little piece of this little trick. The limiting reactant is equal to what? The moles over the coefficient. Now, I have to stress this. This is only used to identify. You cannot use it for any data calculation or anything. It's only used to help us identify. Now you can use the moles part, which will be helpful, but we're only going to use this to identify. I am going to need your help. Some of you are probably already ahead of the game, which is fantastic, but I am going to need your help in calculating some of the moles of this. So, yeah. So 24.3 grams, 1 mole, and then 10.3 grams, and this is 18.02 grams in 1 mole. Does anybody have the current mass of aluminum nitride? Actually, let me back this off. Go ahead. 40.99. Is that too small, too thin for y'all to see, or can y'all still see that? Okay. All right. Makes it a little bit easier for me to. Yes, sir. Okay. Yeah, I need to go back. 0.57. Okay. So those are my number of moles. Now, you guys are intelligent enough to know at this point what is going to be our limiting reactant. The bottom one. You can tell that simply because, number one, it's already less, so what are we fixing to do to it? We're going to divide it by 3. So we're going to divide the top one by 1, and we're going to divide the bottom one by 3. So that automatically tells me that water is my limiting reactant. If that is now, you're going to hear me say this a lot the rest of the year. For my stuff, do you really need to punch all that in and write it all down? We're just trying to find it. May 1st, what do? That's the day of the exam. Write every dadgum thing possible down. I mean, if you have to show long-handed algebra, show it. Okay? Write it all down. You don't want to leave something out that may cost you a point. We're trying to earn points. We're not taking points away. Okay? So show it all. Show all of your knowledge. All right, so here's what I'm going to do. Do you agree that I found the moles so I can use that value? Are we cool with that? Okay. So now we're going to take the limiting reactant. We're going to say that we had 0.572 moles of H2O. And what are we going to do with it? Okay. got mole of H2O to mole of AlOH3. Can I stop there? Nope, one more. Mole of AlOH3. Oh, I did that wrong. Wow. And to grams of AlOH3. Just out of curiosity, I do not care. Do y'all like the fatter print or the thinner print? Okay. That doesn't matter. I'll do whatever you guys want me to do. Huh? The way I like write my letters is better with the thin. Okay. So where does mole to mole come from? Coefficients. So what's it going to be? Alright, so 1 over 3. And anybody got the mass of aluminum hydroxide? So 78.01. Well, now this is an easy calculation. Now, let me go back and ask you something. And I'll pause for just a second. Let you get caught up. Okay, so let me ask you this question. And I'm going to circle it in red. Once I determined what my limiting reactant was, did I have to go back and originally start with that number? Could you have? Yes, but you would have had to have redone that entire step. So, instead of having to redo a step, you can use that value because it's already in moles to run it out. Alright? Now, what is the grams of aluminum hydroxide right here? 14.9. Actually, let's go back and look. We've got 3 sig figs, 3 sig figs, 4 sig figs. So we only need 3. So 14.9 is correct there. And that is grams of AlOH3. So that is theoretical, correct? In theory, if I gave you that exact amount of stuff, in theory, you should get 14.9 grams. However, if this were done, according to this, how much was actually recovered in this experiment? They do a good job or a bad job? It's a really bad job. Okay, so let's go back to this slide right here, and I'm going to plug these numbers in. Help me out. It was 2.0 what? 15 divided by 14.9 times 100, and they gave you what percentage? 13.5. They need to redo their lab. Okay. Well, then they did a really good job. Okay. So here's the deal. This is a long, drawn-out process. I agree with you. It is. It's a challenging deal. But you have to start somewhere, and you have to be able to fight through all this stuff. And think about how much you just did. Think about knowing how to calculate a formula mass. Think about knowing how to convert grams to grams, knowing what a mole to mole is, knowing what a limiting reactant even is, then finding the limiting reactant, then knowing what a percent yield means, knowing its parts, knowing how to plug those parts in, and knowing how to solve for the final answer. It's a lot of chemistry you guys just did. Yes, ma'am. Okay, absolutely. Yes, ma'am. Yes, ma'am. Yes. Okay, so to identify, simply to identify what the limiting reactant is, we do the number of moles, which would you agree, we convert grams to moles, which are those two brown numbers right there. Then we divide it by the coefficient. It's simply just an identification process. There is a lot of extra steps that could go into it, but I don't teach those extra steps because this is simple, straight to the point, you get your answer. Yep. Can I tell you, I don't want to confuse any of you, but I think you guys are all mentally at the point where you can understand this. Some teachers, the way they teach limiting reactants is they take both initial starting amounts, run both of them to the end, and whichever one is least is their limiting reactant. If you want to do that, that's fine. I'm just not. I would much rather go about it this method. And can I be perfectly honest with you? There are a lot. There are a lot of AP problems that I have noticed that they actually give you the masses for the compounds, which is spectacular. You don't actually have to calculate them. So, any more questions on this? Okay. All right, so let's go on to let me read them real quick. All right, so objective for number 3. Again, practice makes perfect. Go ahead and see if you can write a balanced chemical equation for number 3. Okay. All right, so again, we'll spend some more time going back through the acid namings because I know that it's going to be a big deal, and there's some confusing aspects of it. So sulfuric acid is H2SO4. Again, I'm just going to say it out loud. If the acid has the ic ending, it came from the 8 polyatomic, and so sulfuric came from sulfate. Lead 2 acetate, I would expect you to know how to do that one. Then lead 2 sulfate, I would also expect you to know how to do that one because lead's a 2 plus and sulfate's a 2 negative, so they cancel. And then acetic acid is just the H with the acetate on the front of it, or the H on front of the acetate ion because it's hydrogen 1 plus, acetate 1 minus, and so that's where you get that. And it's super, super simple to balance, and just throw a 2 on it right there. Throw a 2 on the acetic acid. Okay. You're cool. You're good. All right, so that is. Now, this is something that I didn't really do a whole lot last year, but I want to go ahead and jump into this part of it. It said solutions of sulfuric acid and lead 2 acetate. So if we were to do this correctly, what would we write behind both of the 2 reactants? AQ. So that is AQ, and that is AQ. Yes. We're actually fixing to. I'm gonna show you a net ionic. We'll talk about it in a second. And it says reacts to form solid lead 2 sulfate. So how would we do that? We would do an S, and then actually, technically, truthfully, they really need to be in parentheses, so it doesn't look like it's a part of the formula. And then acetic acid. What do we know about all acids? They're aqueous. Very good. All right. So here's the deal. And I'm throwing a really big Velcro ball at you right now, just seeing if it sticks. So when we get to net ionic equations, it's going to make a lot more sense. So here's what a net ionic equation. What is a net? What is someone's net worth? It's how much they're totally worth, right? So what a net ionic equation is the ions that are the only thing that actually react. Sense? Okay. A net ionic equation are the ions that are the only things that are reacting in a reaction. Okay. Now this is reaching way back. How many signs are there that a chemical reaction occurred that you can see with your eyeballs? How many? 5. Thank you, Trevor. 5. I've heard color change, bubbles, oxidation, solid precipitate, temperature change, heat and light. Those are the 5. So one more time. Heat and light. Now, when I don't like the word heat, simply because is something getting colder also a temperature change? Yes, so I prefer temperature change in light. Okay. The second thing is bubbles. Okay. Fizzing bubbles. Second thing is color change, oxidation, and what is the name of iron oxidizing? Russ, what is the name of silver oxidizing? Tarnishing. Is there any other? What is lead? No. What it? I think it's copper. What is the name for copper? It's patina. 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 And then the last one is solid precipitate. So, I want you to visually think about what happened. If you could say, all right, this just happened. I had an aqueous solution of sulfuric acid, 1 beaker. I have an aqueous solution of lead acetate in another beaker. And when I poured them into a beaker together, what happened? Very good. This solid precipitate forms along with another aqueous solution. So here's the deal. Here's the biggest problem students in first year chemistry have with that word solid precipitate. They literally think it turns into a rock and sits at the bottom. It's completely far from that. It is very, very tiny speckles and fragments of solid particles. Okay? Yes, sir. That's exactly right. Okay? Eventually, now this is important. Listen to how I phrase this. Eventually, it could all possibly settle to the bottom. But what do we know about the density if it settles? It's higher than 1. Okay? So that's something that has to be also a part of it. The density does make a factor in how much of it settles. But we could pour these two things together, leave it there for a day, and come back, and eventually all the particles would be at the bottom. And I'm kind of adding extension to this. How could I then get the solid particles out? Strain it or filter it, right? Take a coffee filter, pour it through, it will stay in it. And will some of the particles probably fall through? Yes. Take it, the catchings, and just pour it through again, and the top stuff, the sediments, will catch it the next time. But let me ask you this, and this is important. If once we pour through the coffee filter, is the only thing in that filter just the solid particles? No. No, I'm not talking about that. There's still some sort of water that's left, right? So how could we then get rid of the water? Dry it out. Okay, either by heating it up in an oven or a Bunsen burner or some fashion to dry the water molecules off, which is called a dehydration. Yep. Yes. 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 As a matter of fact, that is one of the solubility rules. Is silver chloride is a solid precipitate. Yes. And we'll learn those. So, what I'm trying to get you to understand out of this about net ionic equations is, technically, in the beginning, what did the solution of sulfuric acid look like? Alright, that's a bad question. If I had a beaker of H2SO4 aqueous, if I could take the world's smallest microscope and look inside that liquid, what's in it? Say it again. Ions. If I broke this apart, what would the ions be? If I drew that, is that right or wrong? Wrong. That is now correct. Would you agree? Charge-wise, it has to maintain its balance. Now, obviously, there are a lot more than than 2 hydrogen and 1 sulfate in that entire beaker, correct? There are moles of them. And what is a mole? Exactly. You got it, okay? So, there's lots of those floating around. Not only that, if I take the other beaker, which is filled with lead 2 acetate, correct? It's definitely lead 2. It's important that we know that. So, same thing occurs. If we take the world's smallest microscope and we zoom in on this thing, you're going to have lead 2 floating around, and then C2H3O2 minus, C2H3O2 minus floating around. Would you agree with that? Okay. So here's the deal. When we pour these two things together, something happened. Now, I am going to over-dramatize this thing, but let's pretend that it sits there for an hour. Okay? Or excuse me, 24 hours. And then all along the bottom, we have this solid thing occur. All these little bitty baby tiny particles kind of settle together and look like a big clump of solid. What's that solid made up of? Lead sulfate. So this is PbSO4. Is there still anything out there floating around? What? Hydrogen ions and C2H3O2 minus. Yes. So do you agree that the first beaker, that we had hydrogen and sulfate floating around? Okay. The other beaker, we had lead and acetate floating around. But when we poured them together, a reaction occurred. How do I know with my eyeballs a reaction occurred? A solid formed. Okay? So, because the solid formed, that means something had to react. So let me ask you this again, and I told you this a minute ago. A net ionic reaction is the result, of which ions reacted in this particular reaction. So what you're looking for is which things changed. What looks different from beginning to end. If it looks different, it must stay. If it looks the same, we get rid of it. So is there anything up there that looks identical on both sides? The hydrogens and the acetates. So the things that, actually let me cross these off too. So the things that remain are the things that changed, correct? That is the net ionic equation. So if we rewrote this correctly, we have this plus what's left here and what we formed. That is the net ionic equation. Bingo. You know what we call those things that do nothing? We call those spectator ions. Okay, now what is a spectator? Hydrogen and acetate are hanging out just watching things go on. Okay? We technically don't need them. So what we're going to run into later on down the road is you're going to see stuff like this and written in red. What I need you to understand is there are other things there, but do they matter? If we're going to watch a football game, does it matter how many people are in the stands? Is the football game still probably going to take place? Absolutely. Doesn't matter what happens. The reaction is still going to take place. We don't care who's watching. Okay? So that's what net ionic reactions are. And the things that we don't care anything about, they're just hanging out watching, are called spectator ions. And we'll learn more in depth of who the spectators are and who the actual players are. Yes, sir. They're there. How did they change? By formula. But what about by actual species in the beaker? They're not attached because they're aqueous. Remember, what do you have to have aqueous solutions? You got to have ions in solution. Okay? And you will learn that hydrogen and acetate do not form a solid. They will not connect. And let me tell you why. And I think this will help your brain work a little bit. And I think I may have said it here or not. You're going to hear me refer to this a lot as water is a piranha. Okay? A piranha. Really, I'm making this term more understandable. Okay? That word right there is really what I'm referring to. Water is a piranha is basically telling you that water has really strong hydration forces. So here's what happens, Justin. And I'm not going to draw this in beautifully, but what's going to happen is the water molecules are going to surround that thing, and the water molecules are going to surround this thing, and they're going to keep them from hooking up. Okay, the water is strong enough to do that. Bingo. That's exactly right. So, lead sulfate is stronger of an ionic bond than the hydration forces are. And that's what allows things to make solids or not make solids. Is it stronger than the water? Really, that's what it boils down to. If it makes a solid, it is stronger than the hydration forces. If it doesn't make one, it's weaker than the hydration forces. So let's think about it this way. He said something earlier that I think is interesting. He said that alcohol is a universal solvent, right? It does dissolve. What if we had 100% pure ethanol? Okay, the only thing in there was ethanol. Ethanol is also a solvent. Ladies, what would you use an alcohol base for? Nail polish. Okay. I was thinking nail polish. I should have said specifically. Beautification products. Okay. So it's filled with acetone. Acetone has an alcohol base in it, right? So it can dissolve certain things. So if we were using an alcohol-based thing, alcohol also has we'll call it an alcohol force. I'm not going to call it hydration because what is hydration? Water. It would be an alcoholic force per se, right? So for something to become a solid in an alcohol-based solvent, it would just have to be stronger than the alcoholic forces. That make sense? Okay. So whatever is dissolved in, it just has to be stronger than the majority of what is dissolved in. Is that cool? Dustin. No, this has everything to do with forces, hydration forces, which I guess you could, in essence, tie it way back down to that, but I really wouldn't go that far. Yeah. You could say that, but I don't necessarily know why or how it does it, but it does. Trevor. That's another really good point. Do you want to go that far today? Do you know what that is? All right. So here's what this is. What Trevor asked, and I'm gonna go back and show you. And I'm assuming this is where you were going with this. If not, I just really hurt all of your brains. What I'm assuming you're asking is, why does this hydrogen not hook up with those waters? Is that what you're asking? Okay, so if that's the case, then I'm going in the right direction. This does happen. Okay, that does happen. And guess what happens? When you see hydronium form, this occurs. Which tells you what about hydronium? It's an acid. Bingo. So, I promise. Yes. And I told you I didn't want to get too far. But these are things that we will get to. But if you've seen them now and you hear the word hydronium, and you know that hydronium is an acid because the pH goes down, these are all really good foundational things. So when you hear it the next time, you're like, I remember that. Go ahead. Yes. They're all dissolved in the water. So really, Mason, to make it make more sense, no, that's a good question. Hold on. That's a good question. When you write the letters AQ behind it, it is understood to be with water. Just like whenever you're writing a balanced equation, If there's not a number in front of the formula, it's understood to be a 1. So when you see AQ, it is understood that water is present. Question? No. Okay. But that's fine. I like doing that. I'm not going there. Not going there. All right. Hang on. So here's the deal. The last thing that I want to point out about this. Remember we talked about at the very beginning there are 5 signs of a chemical reaction. One of them that is visible in this particular specific reaction was the solid forming, correct? Okay. The other one, if you add a certain solution to this, called an indicator. Indicators change colors based on pH. Right? So, this is something that I want to point out. And I need you to do something. I need you to ignore this for just a second. This is true, but ignore it for just a second. Sulfuric acid was one of the original solutions, right? And you may or may not know this, but if not, we're going to add a small little token to your base of knowledge. There are 2 types of acids. What are the 2 types? Strong and weak. That's it. There's only 2 types. How many strong ones are there? 6. Is sulfuric acid one of them? Yes. Is acetic acid one of them? So think about it for just a second. We went from sulfuric to acetic. Did it become more acidic or did it become less acidic? Less. So if we had an indicator in the beakers, the color would have changed, correct? It would have gone more towards 7, more neutral. It would have gotten a little bit greener. Okay? Those are things that we'll all learn. But I just want to point that aspect out of this as well. So we've covered a lot in this one question. But all of this will make sense. We're going to hit all these things later on. Yes, sir. Yes, sir. It is the sign. It will. I'm going to think of the best way to respond to this question. Does anyone know what that means? Here's the great news. All you have to do with this is punch it in the calculator. All you literally have to do is punch it. But the reason I wrote this, Justin, is for you. So if you don't want to hear this, don't listen. Whenever we try to determine the pH of a solution, we're counting how many hydrogens are in that solution. So what you just need to understand is that this is equal to that. So when we're trying to determine the pH, you can either count the hydrogens or you can count the hydroniums, and it will give you the pH. So the more of these that are present, now this is the tricky part, the more of these that are present, what happens to the value of the pH? It goes down. That's the weird odd part, that it's backwards. And why is it backwards? Because it's a negative log. Does that make sense? It's kind of weird. The more of these we have, the more acidic it is, but the more acidic something is, the lower it goes, right? Because sulfuric acid, actually I can show you. No, this is really good. In this beaker, remember I just told you, when we're counting the pH, we're counting the number of hydrogens. This beaker had how many hydrogens? This one had how many? Here's your answer. There's more hydrogen, so it's more acidic. And the fact that sulfuric is strong and acetic is weak is another major factor.